In this lesson, we're going to go over optimization problems. Optimization problems are what many people would call word problems, where we have to minimize or maximize some unknown variable like cost or area. So the easiest way to explain an optimization problem is with an example. So let's take a look at this example, and as we go through this example, we'll take note of general guidelines that we can follow, and then we'll outline those guidelines in an upcoming slide. So here we have a manufacturer needs to construct a box having a square base that holds 100 cubic inches. We want to find the dimensions of the box that would minimize the amount of material needed to construct the box. So the first thing that you want to do when you're faced with a problem like this is, if possible, draw a picture and label variables. So we want to construct a box with a square base. Let's label the base sides as X, and we'll call the height H. So we drew a picture, we labeled unknown variables. Now we need to come up with an equation that relates the amount of material needed to construct the box to these variables. So what are some equations that relate to this box? Well, we have a volume equation, and that's going to be good to use because you notice in the problem it says the box is supposed to hold 100 cubic inches. That's a volume. So the volume of a box is length times width times height. So in this case, our length and width are both X and our height is H. So our volume is going to be X times H. And that is supposed to equal 100. So we'll set that to 100. Now the amount of material needed to construct this box, that's the surface area of the box. Now if we look at this, the surface area of the box, we have to add up the areas of the sides of this box. The area of the front of the box, right here, that's just going to be X times H. And we have 4 of those, right? So our surface area is going to be 4 times X times H. Then we have the area of the bottom and the top. Now the bottom, that has dimensions X and X. So the area of the bottom is going to be X squared, and the same for the top. So we're going to have 2X squared. And there's the surface area of our box related back to our variables X and H. Now what we want to do is this. We have to identify, what do we want to minimize? Well, the S is what we want to minimize. That's what we want to minimize. And it would be nice if we could have this S only in terms of one variable, because we know how to minimize a function of just one variable. That's what we've been studying when we find relative and absolute extrema. So how can we get rid of one of these variables? Well, if we look back to this equation up here, we see that we can write H in terms of X. Notice that H is 100 divided by X squared. So we'll take this and substitute it in place of the H right there. And then we'll get our S in terms of just one variable that we can, and then we can minimize S and find out what X value will make S a minimum. So doing that, we get 4X and then simplifying that, the X's here cancel, and we get 400 divided by X plus 2X squared. Now let's identify the domain of this function. Notice that x can actually take on any value from 0 all the way to infinity. If x were very close to 0, this box would be a very tall and skinny box if x were very close to 0. And if x were very large, it would be a short and very wide box. So our domain is actually all x greater than 0. So that's our domain. Now what we want to do is we want to minimize s over this domain. Now our function s is going to look something like this. And so what we want to do is we want to find where s has a minimum. Well, how do we find where a function has a minimum? Well, that's going to be where its derivative is equal to 0. So we have to find where the derivative of this function is equal to 0, and that's going to be the x value that makes s the smallest, and that's what we want to find. So all we have to do is take the derivative and set it equal to 0. So if we differentiate s, we get, remember this is 400 times x to the negative 1. Derivative of x to the negative 1 is negative 1 over x squared plus 4x. And we'll set that equal to 0 and solve this for x. Taking the 400x squared over, negative 400x squared over, we get and now just multiplying the x squared over to the left side, dividing the 4 to the right side, we end up with, and so we get x is the cube root of 100, or 100 to the 1/3 power. And that is approximately 4.64. So that's the x that makes s a minimum. Now technically you should check that this really is a minimum, because if you accidentally maximized it, that wouldn't be good. So just double checking that. Now you're not going to have to do that for every problem. I just mentioned it this one time. For all of these problems that we do, once we set our derivative equal to 0 and solve for our variable, that will be our solution. But technically we should check that this is a minimum. And notice that if we put 0 here and our location where our derivative was equal to 0 is 4.64, put that right here. And then we pick test values like 1 and 5. And if we put those into our derivative right here, if we put 1 in for x, notice we'll get negative 400 plus 4, that is a negative number. And if we put 5 into x here, we will get 20 minus 400 divided by 25, and that will be a positive number. Once again, putting the 5 in here for x, 20 minus 400 divided by 25, and that is what? That is negative 16. So you get 20 minus 16. That's a positive number. So now what this is right here, this is our sign of f of s prime. And so this means that our function s is decreasing and then increasing. And so yes, at 4.64, or the cube root of 100, that's where s will have a minimum. So we found the x value, the dimension of our base that will minimize the surface area. Now we just have to find the height h. Well, you just have to plug 100 to the 1/3 power in here for x and solve for h. So now solving for h would be 100 divided by 100 to the 1/3 power squared. That's going to be 100 to the 2/3 power. and that is also, using our rules for exponents, this is going to be 100 to the 1 minus 2/3, and that is 1/3 as well. So we see that our height is the same as the dimensions of our base. So this is also 4.64. So there we found the dimension of our base and our height, and they actually turn out to be the same. And that makes sense if you think about it for a second. So the dimensions of a box that minimizes the amount of material needed to construct it is a square box, one in which the length, width, and height are all the same. Now let's take a look at some general guidelines that we use when we're solving these optimization problems, just taking note that we really followed those guidelines as we were doing this example. So here are the guidelines that we can follow for solving optimization problems. The first thing you want to do is draw a picture if appropriate and label all appropriate variables. Notice that we did that in the previous example when we drew our box and labeled the x and the h. The second thing you want to do is identify all given variables and all variables that need to be found. Usually there will be a single variable that has to be maximized or minimized. So in our box problem, we had the x and the h, we identified those, and then we identified the volume of the box and the surface area of the box. And the volume of the box was a fixed constant, 100, and the surface area was the variable that we wanted to minimize. Then, step 3, find a primary equation that relates the variables to be maximized or minimized to the other variables. So that's when we took our s and wrote it as a function of x and h. And we also took our volume v and wrote it as a function of x and h as well. Then step 4, you want to reduce the primary equation to a function of only one variable. This may require using other equations given in the problem setup. So remember, that's when we took the s and we got rid of the h variable that was inside of it by setting our v equation equal to 100 and solving for h in terms of x. And then we substituted into our s and we turned the s equation into just an equation with one variable. Then determine the domain of the primary equation. That's when we said that, well, x can go from 0 to infinity, and maximize or minimize the equation over the domain using the techniques previously studied. That's where we differentiated the s and set it equal to 0 and solved for x, and that gave us where s was a minimum. So you notice how we followed all of these guidelines when we did that previous problem. And these are the guidelines that you'll generally follow for all of the optimization problems that we do. So let's take a look at a few more examples. So in this example, an aluminum can needs to be constructed that can hold 150 cubic centimeters. The cost of aluminum is 3 cents per square inch for the side of the can and the bottom of the can, and 5 cents per square inch for the top of the can. We want to find the dimensions of the can that minimize the overall cost to construct the can. So the first thing we want to do is draw a picture. And we'll label the radius of the can right here, we'll call that R, and the height of the can we'll label as H. Alright, now let's looking back at the problem, we want to find the dimensions of the can that minimize the overall cost to construct the can. We're also given that the can is supposed to hold 150 cubic centimeters, so that means we want to find the volume of this can. So the volume Now the volume of a right circular cylinder like this is going to be the area of the base. Now that's going to be pi r squared. You have to remember the area of the circle. So it's going to be pi times r squared. This is the area of the base, which is the area of the circle, times the height. So that's our volume, and that's equal to 150. Now we want to minimize the cost of the can. Now the cost equation, well, let's see. The cost of aluminum is 3 cents per square inch for the side and bottom. So we need to try to figure out the area of the side of the tin can and the bottom. Well, we already know what the area of the bottom is. That's just pi r squared. So this is pi times r squared. That's the area of the bottom, and we multiply that by 3. So that's the cost of the bottom, because it's 3 cents per square centimeter, and this is the area. Now we have to add the cost of the side of the can. Well, to find out the area of the side, think of doing this. Think of taking this can and slicing it open along a seam like this and unrolling it. And when you do that, what you're going to get when you unroll it is you're going to get a rectangle, right? This is going to be the height of the can, that's the h, and the length of this rectangle is going to be the circumference going around the circle here. Right? That's going to be the length of this side right here. So what's the circumference of a circle? Well, it's pi times diameter, or 2 pi r. So the area of the side is 2 pi r h. So the cost of the side of the can is then going to be 2 pi times r times h. And we need to multiply that by 5 because, by 3, because it's 3 cents for the side as well. Now we have the cost for the top of the can. Well, the top of the can has area pi r squared just like the bottom, so it's going to be pi r squared times 5. So that's the cost for the top of the can. So what we have here is the cost for the bottom and side, and right here is the cost for the top. Now let's simplify this as we've got 8 pi r squared plus 6 pi r h. Alright, that comes from 2 times 3 here, and then pi r h. So this is our cost equation. Now, if you think back to our guidelines, we have our cost equation in terms of 2 variables. We have to get rid of one of these variables. So we'll choose to get rid of the h right here. So we have to go back to our other equation up here, and we'll use this to solve for h in terms of r. Well, dividing the pi r squared under the 150, we get that h equals and now we'll take this and put it in place of the h right there. And so our cost equation simplifies to and we can simplify this a bit, and we get and this is the function that we have to minimize. Now notice that r can go from close to 0 all the way up to infinity. If r were close to 0, this tin can would be very tall and thin, and if r were large, it would be a squat tin can, sort of like a tuna fish can. So we want to minimize this over r from 0 to infinity. So we'll take the derivative of this, and we'll set the derivative equal to 0. So if we take the derivative, we get and we'll set that equal to 0 and solve for r. And that's going to be our solution for r. So solving this for r, we get that should be a square right there. Taking r squared over here, combining with this r, dividing the 16 pi over, we get that r. That's going to be r cubed is going to be 900 over 16 pi. And then solving this for r, just taking the cube root of both sides, we're going to get that r equals 900 over 16 pi to the 1/3 power, or the cube root of this. And if you evaluate that on your calculator, that's approximately 2.62, and that would be in centimeters. Now this is where your cost function has a minimum. Technically you should verify that using a number line. If you look at the sign of C prime, you don't have to do this every time you do these problems. If you 2.62, if you pick test points like 1 and 3 and you plug these numbers into the derivative, you see that when you put 1 in to the derivative, you'll get a negative number. If you put 3 in to the derivative, you will get a positive number. So that tells us that the function c is decreasing and then increasing. So yes, 2.62 is an absolute minimum over this interval. But you don't need to do that for all of these problems, because they're always going to work out where your solution is where your derivative is equal to 0 for the problems we're considering. But it is something that is good to verify. And now that we've found what r is equal to, we can now solve for h using this equation up here, and we get that h is going to be 2.62 squared, which is approximately 6.98. And there we've found the dimensions for the tin can that will minimize the cost of construction. Just one note here, when you're approximating your variables, notice how I approximated r by 2.62 and then put that in here. It's good to try to put the exact value back into any other equations. So when I evaluated 6.98, I actually put in the exact value, or at least the value accurate to about 10 or 15 decimal places that my calculator gave me, and then I approximated that to 6.98. So just be careful with rounding errors. Now let's take a look at one more example. Now here's one that you might want to try on your own. A dog kennel is to be constructed as shown. If 300 meters of fencing is available, find the dimensions which maximize the total area. So the dog kennel is to be constructed as this rectangular region, and then you have partitions running up and down made of fencing also. So try to find the dimensions. We'll label this as X and this as Y. Try to pause the video here and find the dimensions X and Y that maximize the total area, given that you only have 300 meters of fencing available. Now, assuming that you did that, let's go over the answer now. So the area of this enclosure is X times Y, and this is what we want to maximize. Now, we're also given that we have 300 meters of fencing. So if we add up the perimeter along with the partitions, we get that the perimeter is 2x plus 1, 2, 3, 4, 5y. And that is equal to 300. So now we want to maximize the area, so we need to get rid of one of these variables, either the x or the y we want to get rid of. So let's use this equation right here to write y in terms of x and then substitute in here, and then we can maximize a. So from the perimeter equation here, we get that taking the 2x over to the other side and dividing by 5, we get that so that's what y is in terms of x. Once again, just take the 2x over, becomes negative 2x, and divide everything by 5, that number right there. 300 over 5, remember, is 60. All right, now we're going to substitute this in place of that y right there, and we get our area equals x and we'll write that as negative 2/5 x squared plus 60x. Now let's take note what the domain of this function is here. Now this step isn't completely necessary, but you'll see many calculus books include this step. So notice that x can vary from 0, in which case our enclosure is very tall and thin, where all of these partitions are included in here. So it can go from 0 all the way up to 150, in which case your partition is very long, like this. So basically x takes up both of these sides, and if we have 300 meters of fencing, that means we're going to have 150 for each of these lengths, so x can go up to 150. So we want to maximize a over this interval. So you'll see many books include this. However, the solution will still be where our derivative is equal to 0. So now, finding where this has a maximum over this interval, we're going to take the derivative and set it equal to 0. So our derivative is going to be negative 4/5 x plus 60, and setting that equal to 0, that will imply that taking the negative 4/5 x over, we're going to get, and that implies that x, multiplying both sides by 5/4, x will equal so 300 divided by 4, that is going to be 75. So this is what x should be chosen to be in order to maximize the area A. Then to find what y is, you just have to substitute 75 in here for x, and you'll get y. So then y will be negative 2/5 times 75 plus 60, and so that comes out to be 30. And so therefore, we found that x should be 75 and y should be 30. So those are the dimensions that we should build this enclosure using 300 meters of fencing in order to maximize the internal area. Now let me just mention one other thing. You'll see some books do this. Just to verify that 75 really is a maximum over this interval, remember how you determine where a maximum for a function is over a closed interval. You find where its derivative is 0 or does not exist, which is what we did, that's 75, and then you test the endpoints and those critical numbers. So just note that a of 0, if you put 0 in to a right here, you'll get 0 times 60, well that is 0, and a of 150 that is equal to 150 times, well, if you evaluate 2/5, negative 2/5 times 150, you will get negative 60 plus 60. That will be 0 as well. You can just verify that. And a of 75, that is going to be 75 times, and if you put 75 in here for x, you will get back 30 in here. So that will be 75 times 30, which is 2,250. And the units there would be square meters. So that verifies that 75 really is a maximum for A over this closed interval. But like I said, you don't really do that. All the problems that we're working on, the maximum or minimum will occur where your derivative is equal to 0 for the particular problems we're working on. And so here is our answer. Let's look at another problem. Now in this example, we want to find the dimensions of the rectangle with the largest area that can be inscribed in the region bounded by y equals 4 minus x squared and the x-axis. So down here we have a graph of the curve y equals 4 minus x squared. And with this problem, what we want to do is we want to inscribe a rectangle like this. So we just want to do the following here, like this. And that's what our rectangle would look like. And so we want to find the dimensions of this rectangle that will have the largest area. You see, we could make the rectangle look like this. We could make it like this. So long and thin like that, or we could make it tall and narrow like this. Or we could make it some shape in between like the one we started with originally. And so one of these rectangles is going to have the maximum area. You can see here it looks like the green rectangle, this one, has a larger area than the other two that we drew. So what we'll do is this. First of all, we draw a picture and label variables. So let's say that this point right here is x on the x-axis, and this point right here will be y on the y-axis. In other words, that point right there that's on the graph is the point x comma y. And x and y satisfy this equation. Keep that in mind. Now, the area for the inscribed rectangle, as we have shown here, it's going to be 2x times y. Width times height. You see, this point right here is going to be negative x on the x-axis. So this distance here, you see that is 2x. The distance from 0 to x is x, of course, and from 0 to negative x is x. So adding them together, we get 2x. And then this distance is y, because that point right there is y on the y-axis, so the distance from 0 up to here is y. And so area is just the length times the height, or length times width, however you want to look at it. So this is what we want to maximize. Now, what we want to do, of course, is differentiate this, find a critical number, and that is going to be our solution, find where the derivative of this is equal to 0. But the problem, of course, is that we have two variables, an x and a y. So what we have to do is eliminate one of those variables so that we can have this equation written in terms of only one variable that we can differentiate with respect to. So we are given this equation right here that relates x and y, of course. So we're given that y equals 4 minus x squared. So what we'll do is just take this and substitute it in for that y, and what we get is our area is 2x times 4 minus x squared. And there you go. Now written in terms of only one variable, x. And we can now differentiate, set the derivative equal to 0, and find where the function a has a maximum value. Now before we differentiate it, we'll just simplify it a little bit. There we go. And then differentiating this. Now, setting this equal to 0, that's going to be where our function is going to have a maximum. And solving this for x, we get that. Taking the 6x over, dividing by 6, we get. And that implies that x is going to be the square root of 4/3, or 2 over root 3. Now this is where our area function will have a maximum, when x is 2 over root 3. If you really wanted to verify that, keep in mind that the area function here is really only defined for x between 2 and 0. You see, if you look at the graphic over here, x can vary from 0 all the way up to 2. That's where the graph crosses the x-axis. And so if you wanted to verify that that's a maximum over this interval, you would just test a of 0. That is 0 in this case. A of the other endpoint 2, that is also 0, if we put 2 in here for x. And a of 2 over root 3, that's going to be a positive value. That's going to be 2 times 2 over root 3, so that's going to be 4 over root 3 times 4 minus 4/3. And if you were to simplify this, this is 32 divided by 3 times root 3. So that's what the maximum area is going to be. So anyway, we found what the x value is. Now all we have to do is find the y value. Well, if we go back up to this equation up here, you see the y is equal to 4 minus x squared, and that's going to be 4 minus 4/3. That's 2 over root 3 squared, being 4/3, and that of course is going to be 8/3. 12/3 minus 4/3 is 8/3. And there you go. So therefore the dimensions of this rectangle are going to be the length, the distance along the base of the rectangle, that's going to be 2x. Keep in mind this is 2x, so that's going to be 2 times 2 over root 3. So that's going to be 4 over root 3. And the width, or height, whatever you want to call it there, is going to be 8/3. And there you go. Those are the dimensions of the rectangle with largest area that can be inscribed like this. Let's take a look at one more example like this. Now let's consider this example. So here we want to find the dimensions of the rectangle of maximum area that can be inscribed in this ellipse, x squared plus 16y squared equals 4. Now down here we have a graphic illustrating what we want to do. So the blue curve here, that is the graph of our function. And we have in the ellipse inscribed a rectangle. And so we want to find the rectangle that has maximal area. So you see, we can take this rectangle and we could inscribe it like this, where the rectangle is wide and narrow, or we could inscribe it like this, where it is tall and thin, and we see that that has little area, as does this case here. And somewhere in between is an optimal rectangle that has maximal area. So we want to find the dimensions of that rectangle. Now we're going to show you a little trick that you can use to maximize the derivative of a function sometimes when we go over this problem. So let's start out by evaluating the area of this rectangle, and then we want to try to maximize that area. So let's label this point right here x comma y. That is a point determining the upper right hand corner of our rectangle. And let's label some distances here. So notice then that this distance here would be x, and this distance would be y. And of course the total distance from here to here would be 2x, and the distance from here to here would be 2y. So the area of our rectangle is given by 2x times 2y, and of course that is just 4xy. And so what we want to do is we want to maximize this. We want to find the values for x and y that make A maximal. Now we have two variables here, and we'd like to get rid of one of the variables. So we'll go back to our equation here, and let's see if we can rewrite y in terms of x and then substitute that in here. Then we'll have an equation involving only one variable, and we can easily maximize that. So if we take this equation and solve for y, we're going to get and then dividing the 16 over and taking the square root of both sides, we're going to get now of course we should have a plus or minus out here, but we're only going to deal with the positive square root because that's going to be giving us the upper right hand corner here of our rectangle where y is positive. And we'll just rewrite this as so now what we can do is substitute this in place of the y up here, and then we'll have our area in terms of one variable. We can differentiate the function and then find the value that maximizes A. So now A is going to be given by so there's our A function. Notice we have it just in terms of one variable, x. Now let's also notice what is the domain for this function. Well, from our graphic over here, we see that x can go up to 2, and, well, it can go from 0, right here starting at 0. That's where our rectangle would be tall and thin like that. You see there, x is about 0. All the way out to where x is 2, like this. So x can vary from 0 to 2. So that's actually the domain for this function. So let's notice that x varies between 0 and 2. And now we're going to take the derivative of this function and find the value where our derivative is 0, and that's where A will have a maximum. Now here's the math trick. Notice that it's a little bit of a pain to differentiate this function as it sits here, because we're going to have to use the product rule in conjunction with the chain rule. And if we were to differentiate it as it sits here, it'd be sort of a nasty looking function that we're going to have to set equal to 0. So what we're going to do is, instead of maximizing a, we're going to maximize a squared. Now, we're justified in doing that because the function a is positive over this interval. So notice that a is greater than 0 over its domain here. And so wherever a has a maximum or minimum value, so will a squared. So let me just say, since a is positive, then a and a squared will have their maximum and minimum values at the same x locations. So instead of maximizing a, we will maximize a squared. That will get rid of the square root, and then this function will be a lot easier to differentiate. So we're going to find where a squared has a maximum over the interval from 0 to 2. So now, differentiating a squared, let's move over here and note that a squared is going to be x squared times 4 minus x squared, and that is just 4x squared minus x to the fourth. And you see, this is going to be a lot easier to differentiate and set equal to 0. So then and setting that equal to 0 to find where a squared has a maximum, we're going to get that the solution to this is and simplifying this, canceling the 8 and the 4 and an x on the left and 1x on the right, we're going to get that. And that implies that x is the square root of 2. And so that is where a squared is going to have its maximum value, and that's the same place that the a function is going to have its maximum value. And you should double check that a squared has its maximum value here by evaluating a squared of the square root of 2, a squared of 0, and a squared of 2. Well, a squared at the endpoints 0 and 2, they're both going to be 0. So what I'm saying is, check that a squared of 0. That's going to be 0 when you put 0 into the a squared function. A squared of 2 is also going to be 0 when you put 2 in here for x. And a squared of the square root of 2, well, that's going to be positive. That's going to be a number larger than 0. So the square root of 2 is where a squared has a maximum value. So you have found the true maximum. And then, so the dimensions for this rectangle, let's see, we found x. Y is then going to be 1/4. Put the square root of 2 back in here for this x right here, and we're going to get, and so that is just the square root of 2 over 4, so root 2 over 4. And so therefore, now the dimensions of the rectangle, remember the length and height of this rectangle is going to be twice both of these numbers. So therefore the dimensions of the rectangle that has maximum area are given by 2 times root 2 by 2 times this number, and so that's going to be root 2 over 2. So there are your dimensions of the rectangle that has a maximal area that is inscribed inside this ellipse. And let's just check that out graphically here quickly before we go. Notice that we found x to be the square root of 2. That is the value that maximizes the area of this rectangle. And the square root of 2 is about 1.414. Well, notice if you watch this number right up here, that number right there corresponds to the x value right here on the x-axis. When that reaches 1.414, about the square root of 2, notice it does look like the area of that rectangle is pretty large in comparison to the other rectangles. So the rectangle we found is about that rectangle right there. And yeah, that does look like that rectangle has a large area in comparison to the alternatives like this one or this one. You see, it does look like it has a fairly big area. And so it seems reasonable that our answer is correct.